So here we go. But first, as any good chemical engineer would, got a couple chemistry jokes here for you guys. I once told a chemistry joke and there was no reaction.
Where's the joke? Oh,
Yeah.
Very nice. And then a lawyer and a
Okay.
scientist are having lunch together. The scientist orders H2O. To look smart, the lawyer says, "I'll have H2O too." And then when the drinks came, they both took a large gulp and the lawyer died. All right.
that
very
one's
nice.
good.
Yeah, that was
That's
pretty
good
good.
because it does react.
Yes, yes. All right, that's the last one I got. Okay. But I do have one story here. So yesterday after work, I was happily finishing up my material for the night. Was pretty much ready to go. And I thought it would be kind of fun to ask ChatGPT if error surfaces would be a good topic to talk about at a machine learning meetup. So I just asked it, I said, I'm going to present at a machine learning meetup. I'm considering error surfaces. Would that work well? And it said, yes, error surfaces can be an interesting and relevant topic for machine learning. Error surfaces, also known as loss landscapes or cost surfaces, blah, blah, blah. And I had never heard of loss landscapes. All I had heard of was error surfaces. So I did a little bit of a Google and I found, I think I've got it right here. Okay, so I'm gonna try to play this and hopefully the audio comes through. Pretty cool.
Pretty cool.
Cool.
Yeah.
It-
So
We're done for the week. We finished the entire thing before 8 o'clock.
yeah, so I saw that and I was basically pretty shocked because I had never seen anything before like this, and I thought it was pretty awesome. So I kind of like, as of last night, like in the evening, I basically changed what I was going to talk about to like this a little bit. So I've got kind of so first of all, I followed up on that a little bit, and I went to that website of the person who made it. And so I can show you basically. So the first thing I did was, if you google.com or whatever, if I go to error surfaces, most of these things aren't that interesting. It's just like, some lecture notes and things like that. So this is what I had been working with. And then if you Google instead loss landscape, then this is the first thing that comes up. And so this is how I found that video. And this website is super cool. So I think tonight we'll probably go through this a little bit, this website, and then the paper that some of it is based on. So
Hey, Grant.
yeah, go ahead.
So just wanted to make a comment about, so this is the difference between Google search and ChatGPT as well, if you think about it, right? So
Yeah.
loss surfaces led you to the landscape. Is that, or the error surfaces led you to
Yeah,
loss
error
landscape?
surface led me to lost landscape, and Google had never pointed that out. It was just on a whim in ChatGPT that it found it.
Yeah. And then that's what people are finding comparison with BARD as well. But just a digression, but that's an important topic in terms of how ChatGPT is becoming so important for education and learning.
Yeah, I love it. And yeah, I totally agree. So instead of so we can kind of scroll around here, but there's one part here that if you click this method, or no, explore, it brings this up. And this right here is an exploration of these lost landscapes. So I'll go ahead and take a second and describe, because people may not know what a lost landscape is. So if you do, I apologize. I'm going to repeat stuff, but so basically what's happening is your X and Y dimension. Obviously, these are really high dimensions, so I'll talk about how we approximate that. But the X and Y dimension are basically the weights and biases of the network, right? So as we vary our weights and biases, the height, like the elevation, is the loss in the network, right? So of course you want to minimize your loss. So like down here, these are good models, and up here, these are bad models, right? Does that make sense?
Yep.
Cool. So yeah, so like this right here is the loss surface or the loss landscape of a real data set, right? So on this website, you can flip through and click different data sets and different models, right? So these are pretty cool. Like this one, this crown is a ReLU, Mish, Swish, activation landscape. So I can show you that in a second. I can't remember which one we're on right now, actually. I think we might be on this one, just whatever comes by default. But this website has really cool things. So this button, I'll just kind of show you so you can kind of do it on your own. I guess I should slow down. The way I got here, I remember I Googled loss landscape, and then I went to the Explore tab. Okay, so that's how I got here. And then so here, this is how you change your model and your loss surface. And then this right here is how you change some of the parameters, and then your controls, it just tells you what the controls are. So I'll just show you an example. This button right here will do gradient descent, okay? So if I click somewhere on the landscape, you can see it's doing gradient descent down this landscape, and it gets stuck right there, for example, right? So this is showing how your training can get stuck in a local minima instead of finding the real minima. So I can try another one, like maybe click right there. See, it's stuck again.
Hey, Grant,
Like right here.
could you put the models resonate with skips?
Yes. Okay, yeah. So
Well, unless that's jumping ahead too much for you.
no, that's wonderful. Okay, so let's do that. So there's something interesting to show. So like this right here, this is a resonate with skip connections. So if anyone knows what a skip connection is, a residual connection, kind of the same thing. So you can already see just based on this wireframe how much smoother this is. Do you guys see that? And when it really loads, you'll be able to see it. So you can see now it's way less bumpy, right? And if you know, just do a basic Google of what is a skip connection or what is a residual connection, it says it makes the model easier to train. This is why, right? It makes it much smoother and it has less local optima. So when you, for example, run the gradient optimizer, it goes right down in the middle there.
Nice.
Pretty cool. And I actually just like that you can like look up here. It's just cool anyway.
You
But
know,
yeah, so go ahead.
they should be doing these visualizations like in, you know, machine learning 101 type thing, you know, when you're doing, you know, MNIST or something like that. That would be really useful, I think, to explain.
Yeah, I think we actually quite a while ago had a meetup that talked about the residual net and the skip connections and how it changed it, but it was never anything as dynamic as this presentation, nor did it do the little trace that you put on there. That's really cool.
Yeah, that is, you know, this is like, you could explain this to high school students or, you know, even junior high school students, and they'd probably get it pretty quickly.
Yeah, I agree. So I'm glad. I'm glad you guys are interested and like it and stuff. So yeah, and you can like draw a trajectory. I'm not sure what this is for. I think the gradient or the optimizer is probably the coolest part to me, at least. And then, you know, we can try maybe just one more. Oh yeah, I wanted to show this because I think it's cool. This is kind of something maybe talk about a little bit later. But so these lost surfaces is it's comparing what you would get from 3 different activation functions, right? So this is the ReLU, which is like kind of the standard, right? And then this is a Mish, and this is a Swish. So you can see not only are they lower, meaning they're providing lower error or a better network, right? This is basically saying there's more capacity, but they're also, you know, smoother, right? So it's easier to find that minima, right? So these are like research areas. Go Go ahead. Yeah,
And
yeah.
again, another thing that Roger mentioned, I think in that prior one, the flatness at the bottom as
Yeah.
well is a very high. And then again, I don't know if I'm jumping ahead, but just
No, please
visually, as
do.
soon as
Yeah.
I see that is a much more robust model, and it's robust to your starting point. Not only is it smooth, but you're going to end up somewhere in that region. So you don't end up with those models where if you train it with a slightly different hyperparameter, all of a sudden you get a 90% jump in accuracy. You have a much more robust base landing point as well, which is the first thing I notice when I see the shape of these.
Yeah.
Right.
That's
Yeah, totally.
The thing I
That's why
noticed
I
on the ReLU looked like it had a local minima there hanging off that right edge there.
Hmm.
Yeah.
That looks like you could get,
It has a
trapped
few of
down
them.
there. Yeah.
Yeah.
Yeah. Versus the other ones seem like, there's an absolute minima, if you will, there that you're eventually it looks like you're highly likely to get to.
Yeah, exactly.
Yeah.
So I totally agree. And thank you guys for jumping in. I meant to say that at the beginning. I want as much, involvement as possible. So yeah. So I think people are kind of researching these things and how different activations functions would give you a different loss landscape.
Do you know what Mish and Swish are? I'm not familiar with them.
Yeah, I didn't. And of course, what did I do? I just looked it up. But
Using ChatGPT.
no, I that was my
You
instinct,
should.
but I didn't do it because I wanted the image. Oh, I misspelled it. Who knows what Mish is? Yeah.
It's
Mish.
Israeli. Come on now. What's Moish? Give me a break.
Sorry. What activation function? All right, this is much better. So it just looks like this. And I don't really know why, but from my brief reading as of last night,
Oh.
they were saying these are non-monotonic, which of course, they are. They're non-monotonic, but I guess the non-monotonicity gives it a little bit more capacity, which I was a little bit surprised by because I would have thought that it maybe would get stuck in a minima somewhere. So I haven't gotten to give it too much.
I think that's the opposite because it's an activation function, right? It effectively can, in a not entirely a predictable way, and that it's a function, right? But it'll bump you out, right? If you had a landscape that did not have that, and then you compare it with an unexpected, if you will, negative value by being non-monotonic, it makes kind of high level sense to me.
So the other thing is that it's continuously differentiable, unlike ReLU, which is a king. So that's one big difference. The other is,
Does that matter in terms of the underlying math, or does that affect the kind of traversal of the surface?
I think the ReLU differentiation, which is the for the gradient, is pretty straightforward. So I don't know if it really matters, but maybe the only thing I can think of is that if it is close to 0, it will still tend to, because there is a slope seems to be same as ReLU after 0, similar, like just one whatever gradient it is. So it's kind of continuous around 0 as well. So
meaning you don't have jerk at that point.
Yeah, but this has been, remember leaky ReLU, right? Used to start at 0 and then go down, but it didn't go back up, which is kind of interesting, right? It kind of goes down and just continues very, very slowly going down in the y-axis here.
I'll ask ChatGPT and post the answer. Sorry.
So
GPT is the source of all truth now.
I don't know that I could have necessarily predicted this behavior, but if you have a monotonic function like leaky ReLU, and then obviously ReLU is also monotonic, but it's just 0 everywhere for negative numbers, right? So it's a little less interesting.
Sure.
But if it's monotonic, then basically, if you have activations, different values of activations, and you sort them from smallest to largest, okay, from most negative to most positive, after the activation function, they will still be in the same order.
You're just describing what monotonicity is, right?
Well, I guess, yes. But so the thing is, if you look at Mish or Swish or Galu, they all look sort of like this. I don't know what the slight differences are between them, but they all basically look linear in the positive numbers, except maybe if you get super close to 0, and they have this little bump, and then they eventually come back up, so that for extremely large negative numbers, they asymptotically approach ReLU, where it's just 0. Okay, but because of that non-monotonicity, it means that in that little range, it can actually fold over numbers, where a number that has slightly bigger activation could actually wind up with a smaller result than something with a slightly smaller activation, right? And I could not have predicted that this would be helpful, that this wouldn't actually be harmful, but certainly I've seen some people talking, and there was a visualization I saw, I don't know if I could find it, where people talked about, oh, look, we're folding this data over in this region of the activation function. And it's like, okay, if you say so. But anyway, it seems that people are very much won over by the fact that it's not monotonic, that it has gradients that are actually negative in sign, as well as gradients that are positive in sign.
Where mine's going,
Dan?
my mind is going, Ted, is that in all of the different model phases of the last 20 some years, one of the most quizzical things that I think is pretty consistent is when we get to the point where the model kind of works really, really well, or the training methodology, pardon me, that's actually more appropriate, is that the training methodology works really well, adding jitter almost always results in a better result. And that dry has always driven me bonkers. And so it seems like that the lack of being monotonic is kind of systemically reintroducing the unexpected kind of push away from that that highly oversolved version of the problem, essentially.
Yeah, I mean,
Is this from Chat GPT? This is, isn't it?
Yeah.
God damn it, Dev.
Some type of
I don't write that smooth.
Jitter, dropout, randomness is going to force you to have a generalized solution, right? You can't just have this tiny little point local minima that you think you're good for, because things can move around. I never really thought of this non-monotonicity, this little bump at the bottom, as being that, but it could be that it forces it to be a little more general. And then there are other activation functions that are continuously differentiable, but they don't go back up, so they're still monotonic. I can't remember. There was one version of ReLU, I can't remember, like ALU or whatever, which was still monotonic, but it was continuously differentiable. It was curved. It didn't have that hard angle in the middle.
Hey, Grant, if you look at, there's a graph down underneath in the related content. It looked like it compares, no, down below the big graph. Look, that one right there.
This one?
That one looks like it compared in multiple ones. Yeah.
Oh yeah, it looks like it's a paper too. Very tiny picture. Let's see.
Hey, Dev, maybe you can ask Chat GPT to read that paper for us real quick and just summarize it. Thanks.
I've tried that, but somehow the token limitation comes into.
Well, have you ponied up for the $20 a month to use?
I'm paying $20 a month.
Yeah. Are you using GPT-4?
I'm using GPT-4. It started with 100 queries every 4 hours to now down to 25 every 4 hours.
Yeah, I noticed that today too. So I guess we'll have to wait for GPT-5 when we go to from 150 billion to 300 or 400 billion neurons. So.
Buddy.
All right, Roger, I'm sorry to disappoint. I think I'm going to get.
Yeah, no, that's okay. That's all right.
You keep watching me click it if you want. But yeah, so this looks like it's a paper too. It might be interesting, honestly.
Did you just volunteer for that grant? Is that what I heard?
We'll
I heard that.
that
Did you guys hear that? I heard that.
But yeah. So that's kind of we kind of started talking about that because of this image here. Yeah. So this one's pretty cool. And then I don't know. We could probably look at one more if you want. Or there's I don't even know what the different, oh, this one, yeah. Let's see. Is it thinking?
You
Or
broke
to
it,
trying to
Grant.
get that image 3
It's so
times.
low, it's off screen.
Yeah, okay, there you go. Let's see here. Please wait a bit while the current process completes.
So while we're
Alright.
waiting for that, I did ask ChatGPT specific questions with the responses that it gave for the previous query. And I asked it specifically about how can more continuous output of activation function in case of mesh smoothness lead to better performance when training deep neural networks, and how can it reduce the likelihood of overfitting? And it gave some pretty good, decent answers as long as we can trust it without, assuming it's not hallucinating. Pretty good points. One is gradient propagation around uh, the smoothness leads it to reach deeper layers of the network more effectively. I have to think a little bit about that, how that is. But the second one, avoidance of dead neurons, that's a pretty important one. So, and then of course I have to read through the explanation for all of those. But pretty good responses, I would say.
Very cool.
Very cool.
Yeah, dead neurons is a good point.
Yeah.
Yeah.
Okay, so I was gonna so just in my Googles, yeah, so like I got I had totally planned out what I was gonna talk about, and then I found this and now I was totally derailed. Okay, so but I feel like this is almost cooler and important, so I did want to talk about this tonight. So I kind of had a proposal. So like I wanted to maybe look at some of that lost landscape stuff a little bit and the paper that it's based on. I was thinking we could do that tonight maybe. And then stuff that I had originally planned on, we could do it next time if people are enjoying it. I don't want to take too many times, but if people want that. And then there's a couple other papers related that we could maybe talk about. So does at least doing this paper tonight sound like a good plan?
I'm up for it.
Sure.
Okay.
Yeah, that's
So
how we operate here. So go.
alrighty.
Yeah.
So
Lead us.
I'll just show you where it is. And again, this came from just Googling loss landscape instead of error surface. So if you Google loss landscape, I'll show you which paper it is. Wow, my Safari looks like it's really struggling. It's the first paper. It's like 1712-09913 if you Google loss landscape. Are people seeing that?
Yes.
Yeah. Okay, I'll give it another second just so people have time to get it.
This looks like the paper we might have been through. Sully, does that look familiar?
I'm catching up here.
Yeah.
Raj, it does kind of look familiar, but it's
Yeah,
been a
it is.
while,
Yeah, it's been a while. No, it doesn't hurt going through it again. Yeah.
Yeah.
No, I mean, I
I
can,
think this is in fact the exact paper.
But no,
But-
I don't think it wouldn't hurt us to do it, go through whatever.
Oh, yeah.
I love it.
Yeah. No,
Yeah.
I agree.
Yeah. This
I agree.
is. Yeah. This
In
Okay,
fact, Grant, as you were doing your introduction, one of the
Mhm.
things I was wondering is, given that fundamentally transformers have changed the effectiveness of training and the effectiveness of models, I'm just wondering if you did that same visualization comparison between like an RNN or an LSTM, and then you compared it with the same kind of level of complexity model using a transformer, if one of the primary differences is the shape of this. I mean, I obviously it's going to have to go lower because its loss is lower in general, but I'm wondering if that the other parameters of the shape of transformers, the size of the trough, the flatness of the base of the trough, kind of the size of your target at the very, very bottom, the smoothness of the sides, and the lack of local minima, I would have to bet that like ChatGPT's version of this is just fundamentally more robust.
Yeah, that wouldn't surprise. I don't know that much about it, but I've heard like transformers are very trainable, and I think that's kind of what you're saying, probably, right?
Yeah.
Yeah.
Is that captured in these visualizations strikingly, essentially. So as
Yeah.
you were showing those videos at the beginning, I kept thinking, like, my mind kept going to, if we were to compare the models we were using 4 years ago with the ones we're using today, I'd bet they look so much different.
Yeah, I think so too.
Well, I mean, the hard thing is that, right, like even a small CNN still has lots and lots of parameters, and that visualization is only looking at 2. So, you know, you kind of have to, I don't know, play around, or maybe it looks like that no matter which 2 you pick. I don't know, right?
Or you just got to zoom out and see things in infinite dimensions. Ted, please, come on.
Yeah.
I'll work on it. I'll ask ChatGPT to give me some exercises to learn how to do that. But I will say that like every transformer paper that I've seen in the last year uses an activation function that looks like Mish, Swish, Galu, whatever.
Really.
I haven't seen a single one where they didn't use that activation function. I'm sure somebody must have one where they said, hey, for whatever reason, this worked better. But like every time that I can recall looking, it was the same thing.
And as we went through the architecture, you know, the skip connection is, or residual stream is kind of the core element of it. So you'd expect that to have that same smoothing effect.
Okay, so I propose a couple things. So it's judging by what Ted just said about the tons of parameters versus 2 and stuff. That's something they discuss here. So do we want to do this, or do we want to do the original thing I prepared? I'm totally cool with either one. I literally did both. So whatever people want. Do we want to do this one, the paper?
I think you should just pick, Grant. What?
All right.
I mean, this
let's
is
do
your
the
show.
paper.
Yeah.
Okay, doke. Okay, so you just kind of, what they're talking about in this paper is basically how to do that visualization that we just saw, right? So the person who made those visualizations like read this and used this as the inspiration, right? And so these 2 pictures are basically what we saw in that visualization earlier, right? We've got a very bumpy surface over here. And then if you have skip connections, it looks smooth, right? So these are the residuals. This is why it makes it easier to train, right? So that's basically, that's just kind of the intro. And then what they're saying here, of course, we just talked about that, the skip connections provide flat minimizers. And this was actually something that was interesting to me, and I don't really know why it happens yet, but optimization trajectories, so like that trajectory that when you start the thing, where does it go down to the bottom? Apparently it lies in a very low dimensional space, which I don't really know why, but I think that's something maybe we could kind of dig in on at some point. What was this one? Networks with specific architectures.
Can I ask a question about that?
Yeah, please do, Jerry.
In theory, what do they mean low dimensional space? Are they just saying there's 2 or 3 major factors and that's it, or what?
No, I don't think it's that like 2 or 3 weights are very important. I think it's like, okay, let's say you had just literally only 2 parameters in your error surface was your Z direction. So you just had X, Y, and Z. So like a weight, a bias, and a Z, right? Then the trajectory being in a low dimensional space, instead of like wobbling in X and Y to the middle, it would just like go like linearly downward. Do you know what I mean? Like if you looked at the top of it, it would be flat, rather than like if you looked at the top, it would be wobbling around. Does that make sense?
So
Okay.
they talk specifically this for specific structures, like do they mean like resonant like architectures, or what do they mean by specific structures? Would you know? That's okay if you don't know.
No, I don't know off the top of my head.
Yeah.
Oh,
Yeah, so I think what they're saying is if you follow all the gradient steps, you know, whether you're doing whatever, some basic vanilla SGD or some variation of it, whatever, right? But assuming you're just doing like mini batch SGD and you do all these gradient steps, then the lowest possible dimensionality is they may be changing parameters on like all 100 of your parameters at once, but if it were a perfectly straight line, right, then that's like one dimensional, right? And if it's just a curve, then it's 2-dimensional. And if it's a spiral, then it's 3-dimensional. And if it's whatever. So I think they're saying that hypothetically, this thing could zigzag all over the place. And if you have 100 parameters, it could be a very 100-dimensional little knot of a rope finding its way to the bottom. But the reality is, no, they don't. They tend to go fairly straight, until
So it's kind of
where they stop.
It's kind of a low dimensional structure that exists in that high dimensional parameter space.
Yeah, so
But
few
it's a
single
line or a
values.
curve or something. Yeah.
Right. So in other words, there are like few singular values that play the role here, or few eigenvalues that you may, but singular values
Right.
probably.
Mhm.
Yeah, so that's Jerry, you originally asked the question. Does it make sense to you at all now? Did anyone help?
Yeah, it does that. It would be much smoother in those low dimensional spaces, I guess. So still something bothering me just a little bit about it, but continue, please. It'll come to me.
No, yeah, that's fair. Okay, so some of this stuff I didn't get too much out of it, but this part I thought was pretty solid. It's kind of where we're getting into the meat of it. So this is saying the basics of loss function visualization. So it's like, your loss function, tons of dimensions, right? So how do you visualize it? There's a couple ways to do it, is what they're saying. I had heard of this paper by Goodfellow, but basically what they're saying in this one-dimensional case is you take a theta one. So this is some set of weights and biases, right? And some different set of weights and biases. And then you draw a straight line through them in the domain of weights and biases, right? And then you can see a linear, or like a 2-dimensional structure of like, here's your X now, your X, and then this is the Y. So this is the height of the surface at that point, right? If that makes sense. Does that make sense? Okay. So yeah, that's what some people do, and you could then plot it on just like a piece of paper at that point, right? So this is that one-dimensional thing. So what did they say here? Found that loss functions appear to lack global minima along the minimization trajectory. I had read this from separately as well. So when you do this plot, it looks like there are not local minima, but then apparently if you do it in 2D, you realize there's tons of local minima and non-convexities. And so like this one-dimensional case, even though it looks smooth, looks good, once you go to more dimensions, we find that it's actually not good. So I think that's what that's saying. Go ahead.
Grant, did you get intuition why that would be the case?
I don't really know. And from my perspective, if we looked at some of those loss surfaces that we just visualized, if you could slice those down one dimension, they would look bumpy to me.
Right, exactly. Yeah.
Yeah, so I don't understand why that is true, but I had seen this in a book too. So I'm not really sure. I think on this one, specifically this paper, they may have like gone from a solution to an initial point. And if you're going straight from a solution to an initial point, then that might not have as many convexities, right? But if you just pick any 2 points, they would, I imagine.
Yeah, that makes sense.
Hey, Roger, I don't know if this is what they were getting at, but I can easily imagine that if you take one of those beautiful 3D plots that we were looking at, right, and you just cut it and you did the 1D curve along that, there's only so many of those little local spikes and valleys that you statistically randomly are going to hit.
Mm-hmm.
Right? And so I could imagine that just like you might have waviness, but the waviness might really obscure the true spikiness of the right. You'll see a little wave because like let's say there's this little pointy mountain, right? But if you just happen to slide along the shoulder of it, you're just going to see this tiny little bump. You'll never. How often are you going to actually on this one trajectory slice right through the peak of one of those things? Right, either a maxima or a local maxima or a local minima, right? Statistically, I think the odds are relatively slim you're going to hit.
So Ted, we talked about this exact question last time we did this paper, and I think because it's exactly the right kind of devil's advocate to this approach. And if I recall, somebody did some research on this, and basically What I believe they found was that the complexity of these surfaces is so high, and the bouncing what's the word, the terrain, like the craziness of the terrain is so high that you can still generalize from one of these projections and reductions how overall the surface looks. If that and I'm sorry if I'm kind of waving my hands as I'm talking through this, but that was my recollection. Roger, you may remember a little bit more, but I remember that exact question because that's the perfect devil's advocate response to this approach.
Yeah, I don't think it quite answered this question about why is a 1D smooth and a 2D's jagged. But you're right. It's how we're only looking at 2Ds in a large dimensional space, so it doesn't really represent it at all. But it's kind of characteristic of it.
Yeah. So they're, yeah, I don't totally know. Again, I think part of it could be that this one went to a local minima. I don't know. I feel like there would be,
That makes
you know,
sense.
bounciness, but so yeah, this is the 1D case, and basically the premise here is saying that these aren't, like, they don't work well enough, right? And then here, what they do, this approach is what they use throughout the rest of the paper, more or less, right? So they do a similar thing, but they do 2 dimensions, right? So you choose some point in your weight space, right? And then you choose 2 direction vectors, delta and eta. Is that eta? Or nu or something. And then you plot a function of this form, right? And so what it is you have this theta, this position in your weight space, that's sort of like your center point, right? That's like your 0, 0. And then this is a vector, and then this is a vector. And alpha and beta are like your x, y at that point. So as alpha or beta changes, it tells you where in the xy plane you're looking. Does that sort of make sense?
Mhm.
Okay. And then so you're plotting some loss as a function of that. So this is the height, and then this value would show how far left or right you are, and this number would show how far up or down you are, or like y direction, right? So so this is what they're using throughout the rest of the paper, right? And basically what they're saying throughout this part is there's a couple naive ways to do this. So like if you use this method and then you start just plotting things, you're going to come to conclusions that may not be right, is basically what they're saying. So like some of this stuff right here, they're talking about scale and variance and network weights. As I like could intuit what that was, but I like had to Google it and it makes sense. Does everyone know what the scale and variance is? Like if you have network A and you have network B, and all of network A's weights are 10 times those of network B, the weights and stuff are going to look totally different, but the network is going to perform the same, right? So there's, so it, the surface will look totally different, even though the networks are performing the exact same way, right?
So it's offsetting scales. One place is big, then multiply later, it's smaller.
Mm-hmm.
It's like, yeah.
Yeah. And yeah. So I could be wrong. If all the weights are times 10, then maybe that'd make it bigger, you know, maybe 10 times in one section divided by 10 in another section, so
yeah,
on.
that's what they're saying, third line, yeah.
Yeah. And so what happens there is if you naively do this, you're gonna get some plots that don't account for that scale invariance, right? And so what they do is they propose this new method called filterwise normalization right here, filterwise normalization. That's what they're proposing. And it took me a second to figure out what it was saying, but it was kind of like, oh, that's cool. So what they do is they choose some vector D as a direction. So that vector D is one of these. It's one of the delta and one of the nu, right? So they're choosing some vector, and they're saying it's compatible with the dimensions of theta. That just means like, you know, let's say you have 1 million weights or biases. It's just saying D is of dimension 1 million. Okay. And then you normalize that D in a very specific way. And I think this is the kicker. This is the thing that they're proposing. You normalize it in a specific way. And that way is to normalize different portions of D based on the magnitude of the weights in that layer. So I know I just said a lot, but that's basically what this is saying, right? You basically choose some random D, right? And then you scale it by its own magnitude. So now that direction vector, you know, these direction vectors, nu and delta, those are of magnitude 1, right? So that's step number 1. And then what you do is for different chunks of that D, and this is what I think, you know, I literally read this today, and what I think they're doing is scaling those portions of D differently based on the magnitude of the weights and biases in those layers, if that makes sense. So that's why they're saying it's layer-wise normalization. Because I think to Roger's point, you know, if one layer is 10 times bigger, then the next layer is maybe got to be 10th the size. So what this does is it does like sort of the opposite and accounts for that size difference.
Mm-hmm.
Is everyone kind of with me a little?
Grant, when you
Yeah, go
say
ahead.
size difference, do you mean just the total number of neurons in the layer, or are you talking about the magnitude of the values, or both?
Thank you. Yeah, the magnitude of the values. So like this theta is the set of parameters that are used in that section, in that layer of the network, right? And so if those parameters, if the like literally the numbers, the weights and the biases are big, then that's what's changing this scaling.
So Grant, if it's
Yeah,
okay,
yeah.
I think I can take a stab at putting this in plain English.
Please do. Yeah, yeah.
All right.
Hmm.
So let's say you had a simple convolution with just one filter. It's a 3x3 filter, so it's just 9 weights. Okay. So one filter might be 3, -3, 3, right? -3, 3, 3, 3, whatever. And then the other one could be like 10, -10, 10, 10. And to your point, like they're kind of doing the same thing. It's just one of them is got a whole bunch of 3s, the other's got a whole bunch of 10s, right? So what they're saying basically is just, okay, we want to know on the whole layer, what is the average magnitude? That's what the norm of the theta is,
Mhm.
right? And so then what you basically say is, I'm going to take my 3, I'm going to divide by that so I just have 1 for my current value, and then I'm going to multiply it by whatever is sort of the average size of things in my layer. And if the average size of things in my layer is 10, then one step in the x direction is going to be 10. But if the average size weight in my layer is 50, then one step will be 50. Does that sound right?
Wonderfully said. Yeah.
Cool.
Does that help?
No, yeah, that cleanly explains it. Yeah, pretty much what I thought, but yeah, go ahead.
Yeah, nicely done. Yeah, so I'll just say it again. Yeah, so this theta, if it's really big in one layer, that means the direction vector is going to be big in that direction. So like when you're looking at it, like when you're looking at the visualization, like a step in that direction is now of like proper magnitude, right? Wouldn't you say, Ted? Would that kind of, maybe a bad way of explaining it, but
yeah. And actually I was struggling with whether it should be sized based on theta or the reciprocal of it.
yes,
But I
yeah.
trust that they got it right, and so I'm just going with what they said.
Yes.
Right, because like maybe for big weights you take small steps, but I don't know.
Yeah.
But that's
I
the
don't know,
general
Ted.
gist, is that
Ted, you could prove them wrong, and make your name here.
yeah. But you could see that, like, right, if you just said I'm going to vary my vector by 10 steps around my center point, right, just by doubling all the weights, then you're going to get a loss surface that's either just like half or double, and so
Right.
it'll look more spiky or less spiky. So you need to somehow figure out, like, what is the proper scale. And so somehow they just said, oh, the average size of weights in a layer is a reasonable way of measuring scale.
Yeah.
One observation, it's actually not in a layer, it's per filter. This is for CNN and it's per filter.
Yep.
They talk about how to do it, but fully connected later.
Yep. Well said. Yeah. So they're just like breaking it into like individual chunks. So like inside a layer, if it's convolutional, then they do each filter inside that convolutional, right?
Yeah.
Yeah. Yep, that's that part. And then basically what they're saying is this method works, and then any of these other naive methods don't work. Is kind of what they're saying. And so then this is sort of an explainer for it's like evidence for that claim, right? And let's see here. It is widely thought that small batch SGD produces flat minimizers, flat error surfaces that generalize well, while large batches produce sharp minima with poor generalization. So I think that's what Sally was saying earlier, right? You want the like big bowl at the bottom, right? Because it's easier to find and so on, easier to generalize. And people, it's widely thought that small batch gets a better bowl than large batch. And so okay, so one thing that I almost skipped over. So this right here is saying, if you don't like do this normalization, you can't compare two network architectures side by side and so on. But if you do this properly, you can compare things side by side and it like actually has meaning, is what they're saying. Okay, so here was their comparison on this training this data set, the VGG network with this, the Keyfar, I don't know how people say that, 10 classifier. And so basically what they did was,
CFAR.
CFAR?
CFAR.
It's a
Oh,
soft
thank
C.
you. Soft C, I like it. CFAR. Okay, so on the CFAR data set. Okay, so what this is, and it's as with all these images, it'll probably take a second to sink in and maybe you'll have to read it on your own. But so this direction here is basically they did the 1D interpolation method, right? So 0 and 1 are solutions from small batch and large batch, right? So if you do the small batch trajectory or small batch optimization, it'll go down the surface and it'll find some point in weight and bias space. And that's one of these. And then the other one, you do the same thing, but with a larger batch and you go and now you find a different point, right? Ideally they would be the same if your optimizer is working really well, but of course they're not, right? And so this is drawing that linear line between them and looking at how the loss looks in that like trajectory. Does that make sense to people? Yay, nay?
What's the two colors, Grant? I'm trying
The
to
two
see
colors,
what
yeah, the
legend.
red and I'm pretty sure, oh yeah, red is accuracy and blue is loss.
Oh, I see. Okay.
Yeah. Yep.
So given that those are accuracy and loss, that kind of makes sense, right? You have working inverse of each other.
High accuracy, low loss, right?
Right. And then when you go asymptotic, you go off scale one and you go off scale with the other two. So it makes perfect sense.
Yep.
Okay. Sorry, I was switching to another machine here. So what's the x-axis here? Sorry.
Yeah, the x-axis is like direction between the two optimal points. So I'll go ahead and show the picture that I drew earlier or whatever this is worth, right? So let's say this theta is the optimal point we found using small batch gradient descent. And then this theta prime is the optimum value. Well, these are technically arguments, but the optimal value we found with large batch gradient descent, right? And then this is that x direction in the plot, and then this is the y, right? Like the error.
Okay, thanks.
Or loss. Yeah.
And I mean, hypothetically, you don't have to take a straight line. You just have to take a linear path from one to another.
What do you mean?
Right. I'm saying to turn it into a 1D plot, you just need to take a linear path from one point
like
to
a
the
1D,
other.
yeah.
It doesn't have to be straight, right? Like it could be like a circular route or something like that.
Yep. So that's actually something that is in like paper number 2 that we could talk about at some point. Is they found, and I'm going to spoil it, but they found that between 2 minima, right? If you follow the straight line between there, you know, you're going to get behavior like this, right? But there are certain curvatures that if you follow, the whole trajectory along that curvature is about the same error value. So they found that your local mins are all connected actually. It's just not a straight line that connects them, right? Yeah, so what they're showing here is basically that these plots don't work if you use the bad normalization. So what this is it's showing you that small batch has a super good, like a big bowl that's nice, right? So this 1 is theta from the small batch, or this 0 is theta from the small batch, and this 1 is theta from the big batch, right? So here you have a super jagged and here you have a super smooth, right? And so everyone's like, oh yeah, look, the small batch is way better, right? But now we just flip one thing, we flip our regularization, right? And then all of a sudden, the large batch has a better min and the small batch has a worse min. So this is kind of part of their proof that it's like these things are more or less arbitrary if you don't normalize them properly.
So they're
this one
saying
is-
that you get different size weights depending on how you do it. And so
Well, yeah, so
therefore you get different properties.
Yep, so this part has no weight decay, which is just, I didn't know that word, it's just L2 regularization. So if you have no weight decay, these parameters are big, right? And, you know, somehow the big parameters mean that this bowl is big. And then here, if you do weight decay, the parameters are much smaller because you can see the x-axis is different, right? And somehow the smaller parameters make the large batch better. And I don't think their point here is that this is a general thing to take away. I think they're just saying that you can't, you know, you can't look at these and say small batch is better than large batch, right? Because if you flip a small hyperparameter, you know, the amount of weight decay, then it just switches, right?
So in this one, they haven't done the normalization yet, right? So
Yeah, is there one coming up where
Correct.
they do the normalization?
That is exactly the next thing. And here I am saying, oh, I finally get it, because it was all saying that it didn't work. And then I was like, oh, now it works because I do it right. Okay. So yeah, that's what this is saying. If you do the proper normalization, then this right here is a small batch with a huge goalie or whatever, huge bowl, and then here is a large batch. And I think one of their points is it's not as pronounced, right? It's not like a huge difference, but there's definitely a difference. Like this small batch showing the bigger bowl than the large batch is what people think is correct, and it's showing that it's correct as well. Does that make sense?
It looks like it's more of a scaling. I don't even know what we're called scaling, but you know, the curves are essentially the same. They're just smooth, slightly different from my, you know, eyeballing it.
The curves are, yeah, they're the same, but right. So you're saying one is just like smushed this way and the other one is spread out that way.
Yeah. I mean, very technical. The smushed is a good term for that. Yeah.
Yeah.
So I can't see on my screen, but I'm assuming the x-axes on all 4 of those are identical.
Yeah. They're all -1 to 1.
Yeah. And so then they also show the left 2 is small versus big with no weight decay. And just like before, the right 2 is small versus big batch with weight decay. But instead of things going different, they're pretty much the same. So they're saying now, hey, look, we get a consistent result. It's invariant to how you apply weight decay.
Yep, exactly.
Why are there
Well
2
said.
lines on each plot?
Test and train.
Oh, test and train. Okay.
Yeah.
and what is CD and GH for? What is that 5E minus for?
Where are you seeing that?
C, figure 3C. What's
Oh,
the
this
first?
is the weight
That's the
decay.
weight decay.
Ah, okay. That's the
There's a
decay.
pretty small alpha,
Yeah.
right? It's a teeny tiny penalty, like 0.005 of whatever your weight value is.
Yeah, I mean, in some sense, weight decay will help. In the previous plot, right? The reason it became smooth with weight decay was also because it's avoiding it to grow really large, right? I mean, it's making sure that there's a decay for large weights over time, so making it more smooth in the figure 2, if you may. So what was the middle figure in the figure 2?
This one here is just the magnitude of the weights. So I don't think their point is saying weight decay is good or bad. I think their point is when you don't normalize, flipping something as small as weight decay, something that innocuous totally flips the results. Whereas here, if you normalize properly, flipping that same thing does not change your results, right? I don't think it's like they're not trying to make a point about the weight decay,
Yeah, they're not saying whether weight decay is good or bad. They're simply saying that you shouldn't expect small batch and large batch to behave completely reversed when you apply a very tiny weight decay. But yet on those other unnormalized charts, you get that effect, which is like, huh? That doesn't make sense.
So did they compare this with other normalization techniques as well?
Yeah, it had, and again, so just to be clear, this isn't normalizing the network, right? This is just normalizing those directions you're going to make your plot, right? Okay.
Yeah.
And yeah, there's a couple other normalization methods mentioned, and I didn't look at all the papers it references, but.
So let me rephrase the question. So the loss landscape for a normalized, a network which applies one of the normalization techniques like batch normalization or
Again, this is different normalization, right?
No, I understand, but how does the loss landscape look for those in terms of smoothness and the bumpiness?
I think this paper predates batch norm, possibly. It's 2017.
No, I think they referred batch norm in one of the references.
All right, I mean, all right.
Yeah, but
we'll see what
nonetheless.
They say. But what right now we're talking about is how to make your visualization. It has nothing to do with the network itself. Right? So let's just say you drew a diagram and you see this loss thing has got this really pointy, steep well, right? Where you say this is a very pointy local minima. If I just change my x-axis scale, I can make that look as flat as I want. And if I say I'm only going to look, instead of between -1 and 1, I'm going to look between, -0.01 and +0.01. Now this looks like a very gradual flat valley instead of a pointy thing, right? So then the question is, what is the right scale? You have to have some I'm blanking on the word I want to use, but some thoughtful way,
normalized,
not some non-arbitrary way of saying what's the right scale to view this thing. And so they say by using the average value of your weights in a given filter for a CNN, that's your principle. That's the word I was trying to look for. That's your principled way of deciding what's a valid scale to use for your diagram.
Does that help, Dev?
Yeah, no, I get what you're saying, Ted and Grant. I just wonder, and you did point, you were trying to look for that word batch, and I don't know what exactly they were saying, because to some extent, were they saying that it got worse with batch normalization, or it was kind of similar observation? When you search for that word, where it looked.
We're not even talking about any kind of neural network. We're just saying, how do you even devise your diagram to measure the loss?
No, I get that, Ted. That's okay. We can defer this discussion.
Yeah, I think they're gonna get to it. They say, now that we figured out how to do our diagram, now let's do diagrams of different things, right? So I think we're getting there.
Mm-hmm.
So you're asking about like changing the neural network, but we haven't gotten there yet. We were just agreeing on a principled way to make our drawing.
Okay, so let me put the argument this way. So the visualization got better, by applying this normalization to the visualization layer for the weights, right? And the batch normalization makes the learning much more controllable, and that probably is because it's applying some kind of changes for each batch, and in a principled manner, learning what is the change that needs to be applied for all batches, and learn that, so that overall there's smooth learning. So I'm thinking in principle those are trying to, like, one is visualizing it, but in terms when you're applying the batch normalization, you're trying to ensure that it's more smooth in some ways.
I see where you're going now. So yeah, I guess you could connect it. You could say that if the bigger the variation in your loss values, you can liken to the magnitude of your gradients. And so one of the big problems we have when training is exploding gradients. So I guess to what you're saying, Dave, right? If we've learned that the filter has very large weights, then we need to change our scale. You could apply the same thing to say, well, if you need to change your scale, then that means that you're also going to have large gradients, and you need to do that. And so batch norm is going to precisely try to do that, although it is doing it in a different way because it's not looking at the weights, it's actually looking at the actual activations.
Right, and then for each batch, it's different. So
Yeah.
So it's very different in that sense. You're right, but
I do see the connection you're making. That hey, if we've discovered that scale is a problem, maybe we should also be applying that. And then to go totally off the deep end, this is why I'm still shocked that this hasn't like made bigger waves. But I loved that Tensor Programs 5 paper where they talked about how you could do a different scaling factor for your learning rate for basically for every layer, for every whatever thing. And I don't know, I don't hear anybody talking about it. And it just seems like we should be doing this.
It's probably it's incorporated in Python, but I don't know if people are using it as widely. But some of these things take time to first of all, those apply for really big networks. So there are very few people who actually leverage those. Just like deep speed and other optimizations that Microsoft had, they're now coming into some of those big networks and people talk about it. So maybe it will take time.
All right. Well, Grant, we finished our little rabbit hole conversation.
No, that's good. I think so that was actually the place that I had gotten to by the time this started. So beyond here, this is everything before was speculation, and now everything after this is wild speculation. As far as like what I think they're saying is with different architectures, and this is not wild speculation, with different architectures you can get different smoothness, right? So Dave, I think this is what you're saying, like with certain architectures it might be super bumpy, and it might not be if you change the architecture. So for example, batch normalization, right? It would make your surface smoother, right? Because it makes it easier to train. That's what the batch normalization could do. And then as far as I think what Ted was saying about different learning rates and different layers, that's not a property of the loss landscape, that's a property of your optimizer, right? So that would keep your landscape the same, but change how you go down it, right? So those are two kind of different things, but I think they're sort of related as well. And then this is the first time I'm looking at it. This looks super bouncy and I can't remember the word they're using, but like very hard to train basically. And so I think that is probably where I'll have to stop on the paper as of now, because I just haven't gotten to the rest, unless someone wants to take a stab at some of these things. I'd like to kind of flash what I was going to show next week, if that's possible.
I guess you're ready to defend your thesis.
Okay.
Yeah, exactly.
Sounds good. We have about 15 minutes just on a time check. So.
Yeah. I'll probably, I figure we can end early, but I was going to at least, let's see here. Yeah, let's try this. Okay, so has anybody used GeoGebra before? Just curious, thumbs up, thumbs down. Anyone used it? No?
Never even heard of it.
Oh man, this is gonna be perfect then. Okay, everyone's gonna be a GeoGebra master by next week, I hope. But basically it's like a graphing calculator, or and that like way undersells it, but it's really powerful for doing like math visualizations, right?
I would agree with you that it's way underselling it, no matter what it is.
Yeah.
Just in that, like starting out with saying something's awesome, it's like a graphing calculator is not. You've definitely not oversold anything.
Yeah, well said.
Is it same as Desmos?
It's similar to Desmos, but I've gotten way more success with GeoGebra.
Hmm.
Like
Yeah,
you
I've
can do
used
3D.
Desmos quite a lot, and I've heard about GeoGebra, but never got to it.
Okay. So like I just looked myself up, but I think you can find me by doing this. And the reason I say me is because I like started to make, yeah, so that's a way to find me. So like in the search bar, type me in, and then you can like click one of my activities and go to like this, right? And then there's like a book that I made on the stuff that we can talk about next week if people are interested. Just kind of building up how we would make our own loss surface from data, just fake data, basically like 2 data points, and then starting to make a plot, with just a linear function, then an affine function, then wrapped in a ReLU, and so on, and seeing how the loss surface changes. So I think it's pretty cool stuff, and I'll just show you one of the things was I made this one called like Javier's method, and so Javier is the person who made that YouTube video, and so this was my just back of the envelope approximation of what they're doing, and this will be the last thing I show if that's all right. All right, so I'm gonna just turn all these on so you can see how I constructed it, and then I'll turn them all off so you can see it a little easier. So, well, maybe if I just start from the beginning, would that help? And next week we'll walk through making these. So hopefully it'll be kind of cool and people get some experience with GeoGebra. So what I did was I just said, okay, let's start. Let's make ourselves some random direction vector. I just picked this. You could make it whatever you want. That's basically what they started with in the paper, right? So I'm gonna not do the normalization part of it yet because I didn't do all that. This is just back of the envelope, no normalization, right? So now, and we're gonna do it in a 1D space of 3D, or we're gonna do it in a 2D space of 3D, right? Or we could think of it as our domain is 1D instead of 2D, okay? So here's a random point we pick in weight space, right? So maybe this would be a weight and this would be a bias. And now what we're gonna do is take this little vector and go up 1 and down 1, right? Does that make sense so far? Okay, so now this is the direction on which they're plotting things, right? Okay, and so now if we make 2 vertical lines, just parallel with this, so 2 vertical lines, okay? And now here I just made a surface. So this is just, we could call it the loss, the true loss landscape, right? That, and normally would be at super high dimension, but we can only see it in a few, right? So this is the true, and we're gonna slice it, okay? So now, what I did was, I can't remember, oh yeah, I put a point down here so we could move things around, okay? I wonder if I'm breaking things right now, okay? And so then, oh yeah, that's fine, I didn't break anything. So all I did was I made a plane out of those 2 vertical lines. And now what we're gonna do is see where this plane slices our loss surface. So now like that, and so now I'm gonna hide everything again. And all we see is this right here is a 1D representation of what they're doing in those videos, right? So now if we move this around, you can see how that the intersection between our plane and the loss surface changes. And that's what they're doing in those videos. And then of course you try to get to this bottom thing, but I just made some random function, so it doesn't really have one. Saddle point.
Yeah, so this function is not linear in the loss surface, right? So
What's that?
it's not in one direction, it's changing directions, right?
So like if we looked this direction, right? this would be like the 1D approach. So this is very similar to like the graphs we saw in the paper,
Yeah.
right? And so
Yeah.
then this would be +1 and -1 or whatever. Right?
Mhm.
Yeah, and so then in the YouTube video, they just do this, but one more dimension. And then now what's in here is a terrain, and then you're slicing this million dimension thing into 2 domain dimensions, and then your error is your third. Cool. So hopefully next time we can do a little bit more stuff like this, and then we can kind of build them up together and make our own little baby loss surfaces. That should be cool. But I think that's all I've got. And
Okay.
if anyone has
Thanks,
any.
Grant. That's really cool. So
That was
so
good.
just to that conversation we were having about normalizing your picture of the loss landscape.
Mhm.
If we made that vector C that you have right now,
Yep.
if we made it much, much shorter, then everything would seem much shallower, because one step would move you a lot less.
Well
And if we
said,
made
yep.
C super long, then that would make one step huge. And so then it would make it like everything's changing really fast within one step. So you just have to decide what's a valid, principled way of deciding your step size.
Absolutely. Yeah, thanks for letting me eke out a little more juice out of this visual.
Nice.
Yeah.
Can you put the surface back on and do that move?
Yeah,
too?
sure. Yep. So now we can, so if you move this is that scaling, right?
Mhm.
So now if this is tiny, like Ted's saying, I mean, you don't, this looks reasonably smooth, right? But
Mhm.
if this is all of a sudden what you're zooming in, now it's got an up and a down, and there's a lot more, it
Mhm.
to your perception, it looks curvier, right?
Mhm.
Yeah.
Interesting.
And then if we move this thing, right, you see it traces over. Kind of cool.
Interesting. Okay. Anything more, Grant?
I think that's all from me.
Okay.
Thanks, everybody.
Question? Yeah. Thank
Nice
you,
job,
Grant.
Grant.
Yeah,
Good job.
awesome.
Yeah.
Thank you.
Thank you,
Learned,
Greg.
learned
That's
about
really
some new tools today for me. I don't know about anybody else, but
Yeah, soon. And after next week, we'll all be GeoGebra ninjas.
okay. I'm going to stop the recording right now then.
Cool.